Okay, so we were part A, we were asked to derive this expression. Now it's a standing wave, so we have two incoming waves. We have y1, which is a sine kx minus omega t, and y2 is traveling in the opposite direction with phase difference phi, which implies that the equation for it is y2 is equal to a sine kx plus, for the opposite direction, plus phi. And now y1 plus y2 is equal to, when we add these two together, we have 2a sine. Now we need to sum everything in here. Kx minus omega t plus kx plus omega t plus phi gives us 2kx plus phi, and then we need to divide by 2. So that gives us kx plus phi on 2. And then cos, the difference between these things. So when we do kx minus, let's do kx plus omega t plus phi minus kx minus omega t. So we end up with omega t plus phi on 2. So that's how we derive the expression. Part B asks us, what's the distance between nodes? Well, nodes will happen when kx plus phi on 2 is equal to n pi. In that case, this sine function will be 0. So x is equal to n pi minus phi on 2 over k is equal to n pi minus phi on 2 over, now k is 2 pi on lambda. Okay, now the distance between adjacent nodes, let's do x of n plus 1 minus x of n is equal to n plus 1 pi minus phi over 2, 2 pi minus n phi minus phi over 2 pi lambda. Now these are all over the same thing, so this and this will cancel out. This n will cancel this n here, and we'll end up with pi over 2 pi lambda, which is equal to lambda over 2. So separation between adjacent nodes is lambda over 2. Now part C asks us, would the position of the nodes change? Well, yes, it's changed by this factor. We've got the minus phi on 2 here, which we didn't have when we had phi was equal to 0. So yes, it shifts them to the left by phi over 2k. That's the entire additional term.